So for the third topic, we'll look at Newton's method, which is trying to solve exactly the same problem that the bisection method is trying to solve. And it's probably, this is a very commonly used method for solving nonlinear equations, maybe the most commonly used. And the idea is, so in general, I want to find a value x star so that f of x star is equal to 0. And so the bisection method, that was nice because all I needed to assume was that my function was continuous and that I knew an interval so that it was positive at one side and negative at the other. I need a little bit more in the way of assumptions for Newton's method. So for Newton's method, I need to assume that f of x is differentiable. The other thing I need is a starting point. So I need to have some point that's reasonably close to x star. And the idea underlying Newton's method is I want to make an approximation of my function using a first-order Taylor polynomial around a point xk. So what Newton's method is going to do, it's from this starting point x0, so that's sort of, you can think of that as xk with k equal to 0. It's just going to, I want to have some sort of rule to get a sequence of points. So I'm going to, from x0, I want to have a rule that gives me x1. And then I can plug that value x1 back into my rule, and that's going to give me x2. And the idea is I want to build a sequence of points, x1, x2, x3, and so on, that's getting closer and closer to this point x star that I'm trying to calculate. So the idea for Newton's method is I'll take this function f of x, and I'm going to make a Taylor polynomial around the point xk. So I just evaluate the function at xk. So this is the point that I know. And then I have x minus xk times the slope of the function, so the derivative of f evaluated at the point xk, so f prime of xk. And then I want to find a point f of x that's equal to 0. So I'm just going to set this equal to 0. So I want to sort of pretend that this function would be straight enough that if I plugged in xk plus 1, it would be equal to 0. And so the linear function is actually going to do that for me. And what I'm going to end up with is f of xk, so this is just my Taylor polynomial again, then xk plus 1 minus xk times f prime of xk, that's an expression for f of xk plus 1, and that's supposed to be an approximation for f of x, and I want f of x to equal 0. So I'm going to say that's sort of approximately 0. So I'll just set that equal to 0 and use that as my approximation. And then what I'm going to do is solve for xk plus 1. And that's going to give me this recursive formula. So if I just take this, set it equal to 0, and solve for xk plus 1, I end up with xk plus 1 is equal to xk minus the function evaluated at xk divided by the slope of the function, so the derivative of the function evaluated at xk. And again, I made a picture of this, so I think it'll be easier to see what's going on if I just draw it. So starting from this point x0, I want to build a sequence x1, x2, x3 that's going to converge. And so the curve here is my function f of x, and I'm looking for this point x star that I made in blue, where f of x is equal to 0. And so what I'm doing, if you think about this recursive formula, I'm taking f of x0, f of x0, and I'm dividing by the slope of this tangent line to f that goes through f of x0, comma f of x0. So this line right here. And remember, slope is rise over run. So basically, what I know from f of x0, that's the distance from the x-axis up to this point. So that's the rise. And what I want to get from x0 to x1. So I want the run. So all I've done is just sort of rearranged things so that I'm solving for the run in terms of x0 and the rise. And each time I evaluate this, so I move from x0, so I take x0 minus f of x0 divided by the derivative, so f prime of x0, and that gets me this point x1. Then I'm going to take, to get myself from x1 to x2, I'm going to take x1 minus f of x1, oops, okay, I guess I can't select that one, minus f of x1 divided by the slope of this line here, and that's going to take me to x2. And so I'm building up this sort of set of steps that's getting me closer and closer to this point x star. And the nice thing, just because of the way I've drawn this function, you should be able to see that no matter where I put a point on the right side of x star, this linear approximation is always going to be greater than x star. So because the slope of the dotted line, it's always going to be a little bit steeper than the curve to the left of wherever I make the approximation. So just looking at the size of these steps, you can see that the next one, it's going to get us pretty close to this pretty quickly. But the reason that Newton's method is really popular is once we get within a certain neighborhood of x star, we get a very nice theoretical property for how fast Newton's method will converge to the true value x star. So I'll go through that quickly here. So all I've done here, so I've said 0 is equal to f of x star. So I'm making a Taylor polynomial, a Taylor approximation, around the point xk for x star. So I'm building a Taylor polynomial at a point xk. These are the points I know because these are the sequence of points that are coming out of my algorithm, my Taylor's Newton's method algorithm. And then I don't know what this is, but if I did know what it is, this would be a Taylor polynomial for it. And I've also put the derivative form for the error. So I actually have a true equality here. This isn't an approximation. And the only problem is I need this c. So this is some point, and I've drawn this interval for the picture on the last slide. So this c just has to be a point in between x star and xk, but I've just assumed that xk is greater than x star, just to make the notation here a little bit simpler. And so what did I do here? So I just divided both sides by f prime of xk. And so the right-hand side, it's, oh, I guess I also moved some stuff to the other side of the equal sign. The right-hand side looks like it's getting a little bit more complicated. But the left-hand side is starting to look a little bit like the Newton's method iteration. So let's see what happens if I keep going. So what I've ended up with, I have xk here, and f of xk divided by f prime of xk. So this is actually just going to become xk minus 1. And it's negative because there's a minus 1 in front of it. So it should be positive xk minus this. But I actually have minus xk plus this. So that ends up being a minus xk plus 1 here. And that is equal to this somewhat ugly-looking thing on the right-hand side. But if I think about this, what is that? That's the distance between the most recent value in my Newton's method sequence and the true value. So I'm going to think about that as the error. So I'll call this epsilon sub k plus 1. So it's the difference between the thing I'm trying to get to and where I'm at right now in k plus 1 steps. And then if I look at the right-hand side, this is exactly the same thing. It's the distance from where I am in the kth step, so one step before the left-hand side. But this time it's squared. So if I replace these with something else, I'm going to use an epsilon just for the error. I see that the error after k plus 1 steps is a function of the error after k steps squared. And so then what we want to find is, once we're sort of within a certain neighborhood of the true value x star, we'll be able to find what the maximum value of this thing is. So I'll let capital M be just the biggest I can make this thing in absolute terms. Then the size of my error after k plus 1 steps is going to be less than or equal to the size of my error after k steps squared. And so this means when I have the size of my error is getting small, if I have 0.01, that means my next step is going to be 0.01 squared. So I've gone from having 2 zeros to having, I think that ends up being 5 zeros and then a 1. So I'm getting significant digits very, very quickly after a certain point. And so we'll say that because the error is getting smaller at a quadratic rate, we'll say Newton's method converges quadratically. So a few things we need to be careful about with this, though. So the quadratic convergence for Newton's method is not guaranteed. So we have to first somehow get ourselves into this interval where the quadratic convergence is going to happen. And that means you need to have a good starting point. So you can imagine functions where you might take a step and just step over that interval completely, and then maybe take a step the other direction and again step over that interval completely. And you might have to do that for a very long time before you finally get into that interval. But once you're in that interval, it's going to maybe take just 2 or 3 more iterations for you to get to the number that you're looking for. So that's what I mean when I say you need a good starting point. Sometimes there's some extra theory that comes with whatever problem you're trying to solve that's going to suggest what are good starting points. So maybe you can make an approximation for what you're looking for, and then you just want to use Newton's method to refine that, and then everything will happen very quickly. So the first bullet point was quadratic convergence is not guaranteed, and then my second bullet point is it gets worse, which is convergence is not even guaranteed. So in particular, the algorithm can cycle. And so what I mean by cycling is, suppose that it's best just to show off with an example. So suppose I'm trying to find out where sine x is equal to 0 between minus pi over 2 and pi over 2. So everybody knows that it's at 0, right? Okay, so this is something we shouldn't have to solve numerically. I'm just using it as an example of what can go wrong if you did. So there's actually a point x sub k. So when I do my update, I'd have x sub k. And now when I take the derivative of sine is negative cosine. Oops. Have I done this backwards? Yeah, I have this upside down. Yeah, so this should be a minus sign. Boy, embarrassing. So that should be a minus sign. But the idea is still going to be the same. I'm going to do one step. And because I have this thing that has this kind of odd symmetry, so when I say odd here, I mean odd as in a function can be even or odd, not as in it's strange. I'm going to update my xk. And I'm going to get exactly the same value, but on the other side of 0. So I'm going to get negative x sub k. And then what's going to happen is when I plug in x sub k plus 1, that's exactly the same thing as plugging in x sub minus k. It's going to create a step. So the sine is going to flip signs because it's an odd function. But the cosine is going to just ignore the sign on the x sub k because it's an even function. So cosine of minus x is equal to cosine of x. And so that's going to mean that I'm going to step back to exactly the point where I started from. So if I ever happen to hit this number, I'm now just going to be going back and forth between those two numbers for the rest of the algorithm. So when you see implementations of Newton's method, it always has a parameter called max iter or something like that, and that means maximum number of iterations. And so because it has this property that when it does converge, when you do get into this sort of small interval, or you get into this interval where you have the quadratic convergence, it's going to converge very fast. It means that it's either going to converge in about 25 or 50 steps, or it's not going to converge at all. So there's no point, if it's run 50 steps, there's no real point in letting it keep going. You know, so you're just in an area where it's not going to give you a solution. And so generally, you put something like that in just to protect yourself against this, this cycling.